you remember lines of best fit? We did these back in grade 9 when we had scatter plots. And you remember plotting scatter plots, points on a graph or on a plot, and you drew a line that kind of best fit all the data points. So we're going to come back to that idea. And this is called linear regression. So what it is, it's an analytic technique for determining the relationship between a variable and a dependent variable and an independent variable. And and if we can find that line of best fit through those data points, you can do two things. Okay, you can do an interpolation. You might remember this from grade 9. So an interpolation is when you estimate between known data values. So estimate between known data values. Okay, and extrapolation is when you predict beyond the range of data. Okay, so to kind of illustrate this idea, like you imagine here, I'm going to draw on the side here, a quick little sketch of a scatter plot. You have maybe some points around here. So I'm going to draw a set of scatter plot points with an increasing trend. And so if you draw a line of best fit, so here, roughly speaking, is a nice line of best fit for this data. I'm going to extend the line in both directions. Okay, and so here, when we're looking at data, and let's say I'm asked to predict a point. Maybe you're measuring, let's say, time here on the x-axis, and maybe you're measuring speed, car or something like that. Okay, and if you're asked to predict, let's say, the speed of a car at some point here, we call that T1, and there's no data point for it, right? There's no data point, but we do have the line of best fit, and so we can find that estimate of the speed of the car at that particular time, okay? And we use the line of best fit to do that. So then when you find this new point, if this point is between or inside your scatter plot data set, so it's between a data point here on the scatter plot, and it's between this data point here on the scatter plot, that's called an interpolation, okay? And if you are asked to find a point outside your data set, so something, let's say, out here, where this point, this time t, let's call this t2. So this time of t2, the speed for this, let's say it's a car, is not between any 2 points. I mean, there's a data point over here, but there's no data point on the right side. So this is outside our data set. So this point here is outside, and so we call that an extrapolation. This is an extrapolation because it's outside of our range. Our range is right here. This is our range of our data. And this point here is an interpolation. Okay, so visually, that's what those two things mean. Okay, least squares fit. So this creating a line of best fit, first of all, using a least squares fit gives more accurate results, especially for weak correlations. So how do you do a least squares fit? So you determine something called a residual. Okay, basically, how far is that point deviating from the line of best fit? So a residual would be, if you had a point up here, how far does it deviate from the line of best fit? That's a residual. Okay, and continuing on here, residuals are positive for points above the line and negative for points below the line. Okay, the sum of all the residuals is 0. They have to cancel each other out. It kind of keeps the line balanced. And the sum of the squares of the residuals has the least possible value. So if you can satisfy this criteria, you can create a very effective line of best fit. So you can create any equation for a line of best fit using this plot, this method. Okay, and so how do you calculate that? Well, the slope of that line of best fit would be given by this long formula here, and the b value for that line of best fit would be given by this formula over here. Okay, and this will be an important formula for us to use. Now, for the vast majority of our project work, our ISU work, or I should say, we're using the spreadsheets. We're using the software to calculate lines of best fit. Okay, so here, example number 1. Use the table. The table shows data for full-time employees of a small company. Okay, so you can see annual income, On the top, this is the table, the graph for annual income in thousands of dollars, and the age going from 0 to 60. Okay, so use a scatter plot to suggest a possible correlation between age and income. So it looks like there could be a linear relationship here, a correlation. Okay, positive, it's an increasing positive trend here. Okay, and it's, why is this not? All right, there you go. Oop, another line got created. Let's see if I can erase that. Okay, there we go. So I see a very strong. It's strong because the data points are very close to that line. So it's a strong, there appears to be a strong linear correlation. Okay, and maybe this correlation has a R value of 0.9. Okay, linear correlations usually are indicated by an R value, and the closer that R value is to 1, the more perfect it matches the data points. Okay, and we'll go, let's move on. So let's look at calculating this line of best fit. So analytically find the equation for the line of best fit and classify the correlation. Okay, so we have some things here. Okay, so I set this up in a table. If I ever give you a question like this, I'm going to set up a table for you to easily do this. Okay, so you have your ages here. X is your X values, your age. Income is your Y values. So calculate the X squared and the Y squared. And the reason why you need to calculate X squared and Y squared is because it will help you to help us find some of these values. Okay, so 33 x squared is, so 33 squared. This number that goes in here is 1089. Y squared would be 33 squared again, so it's also 1089. And x times y would be 1089. Okay, and 25 times 25 is 625. And 31 times 31 is 961. And 25 times 31 is 775. And as you can see, the rest of the table is already filled in for you. We have done some of this work. Let's add up this column here of x squared. So if I sum together all the numbers here for the x squareds, I get 11,712. If I sum all the values here for the y squared, you get 14,975. And if I sum all the xy's here, you get 13,221. Okay. Okay, so what else are we going to need? I'm going to need some mean values. Okay, so let's, on the side here, calculate the mean value for x. So x is equal to the sum of all the x values divided by the number of x values. So I already have the sum of all the x values. That's 292. And if you count up how many x values we have here, we have 8 x values altogether. So the mean x value is going to be 292 divided by 8. And that's equal to 36.5. Okay, do the same thing for the y values. So the sum of all the y values divided by n, and so the sum of all the y values is 329. Where did I get that from? This column right here. Add up all the y values for income, you get 329. Divide it by 8 because there are 8 y values. So the mean y value is 41.13. Okay. Now let's do some more math. All right, so down here, a value. This is going to help you find the slope of this line of best fit. So let's plug in what we know. So remember, this is the formula that I showed you up here. Okay, so we need these x squareds and xy, some of the x, some of the y. So this is why we did all that stuff here in the table. So let's plug in what we know. So a is equal to n. So n is 8. So there's 8 values here in my table. The sigma xy, we can get that from over here, 13,221. Okay, minus sum of all the x values, 292, multiplied by the sum of all the y values, 329. Then we divide everything, okay, by n, which is 8, and the sum of all the x squared values, we calculated that to be 11,712. and subtract the sum of all the x squared values again, 11,712. Okay, so we take the top 9,000. Sorry, if we add up, if we do the top, if we evaluate the top part numerically, it should be 9,700. Then you evaluate the bottom part numerically, we should get 8,432. And I encourage you to check this on your own yourself. And dividing the top and the bottom, I get 1.15. So there's the slope of my line of best fit. Okay, what about the y-intercept? And the y-intercept B is going to equal y bar minus ax bar. So the mean value of the y, so 41.13 minus the slope we calculated, 1.15, times the mean value for the x value, so 36.5. These two values we calculated on the top, on the right side here. So this is 41.13 and 36.5. Okay, evaluating that, we get a b value of negative 0.845, and we'll just round that to approximately negative 0.85. So therefore, the line of best fit for our data is y equals 1.15x minus 0.85. Okay, so let's look at something called the R value. Now the R value is our correlation coefficient. Correlation coefficient tells us how close does our line match the data point or the scatter plot directly. So the more of those scatter plot points that are on your line of best fit, the more this R value is going to get closer to 1. Okay, if the R value is 0, then there's no correlation. If it's closer to 0, there's probably hardly any correlation at all. Okay, if the R value is negative, then your correlation is negative, meaning the line is going down to the right. So let's find how good is this line fitting this data. It looks like it might be a very good, strong correlation. I'm expecting a number in the range of 0.9 because these points are really close to the line. So let's look at what that R value is going to be. And we have another formula for that. Okay, and the formula to find that R value, it's written right here. So here it is. And we're just going to, at this point, it's just a mechanical operation, just plugging and chugging our numbers, trying to calculate things here. Okay. Now, the first part, we already calculated this. This top part, this part here is the same as the formula for this slope. So I'm going to reuse that number, 9,700. So let's write that here. So R equals 9,700. Now what I have to do is calculate the bottom part. Okay, so let's do a little bit of algebra here. So this bottom part, we also already calculated this. This part here was the same thing we had up here, 8,432. And we get to do the same thing for the y value. So let's just write that down here. So this is the square root of 8,432 multiplied by, so n is 8. The sum of all the y values squared is, so multiply that by 14,975. And we subtract that by delta sigma y squared, so 329 squared. Okay, close that bracket. R equals, so let's do this, 9,700 divided by the square root of 8,432 multiplied by 11,559. And that equals 0.98. Take a moment to pause this video and check that out for yourself. 0.98. Okay, so let's look at the conclusion here. So therefore, R equals 0.98. That's almost 1. Okay, so this implies a very strong positive correlation. Okay, so as age increases, we can say with very strong certainty based on this data, income also increases. Okay, by about If the slope was 1.15 and the y values are in thousands, then we can translate that to $1,150 per year. So every year that you age, your salary or whatever money you make increases by $1,150 per year. Okay, part 3. Predict the income for a new employee who is 21, an employee at age 65. Are these examples interpolation or extrapolation? So let's look at x equals 21. So for x equals 21, we need to use our formula, line of best fit. So y equals, the slope is 1.15 multiplied by x, which is now 21, substituting 21, subtract 0.85, my b value, and solve, and we get 23.3. Or if it's in thousands, we're saying it's $23,300 per year. Okay, and this is an example of interpolation. Why? Because this data point is within our scatter plot, within the range of our scatter plot, right? So our scatter plot starts here. So this is before 20. The 21 is right about here somewhere. So this is in between our data points, and so it is part of our scatter plot. Let me make this quick correction. Our data set starts here with this first point, which is before 20. Okay. So let's look at x equals 65. So here for x equals 65, plugging that into our formula, y equals 1.15 times 65 minus 0.85, and we get a value of 73.9. Okay, or we could say this is $73,900 per year. Okay, and this would be an extrapolation. Okay, and the reason why is because we have no data in our table for those age 65, right? It only goes up to 50 something, goes up to 54. So anything outside this range of ages is going to be called an extrapolation. We're only guessing. We're only trying to predict or estimate what that value would be. Okay, so the conclusion here is, therefore, you would expect a new employee to earn about $23,000 per year, and a retiring employee to earn $74,000 per year. Okay, and this is going to be very important. The extrapolated value, it's beyond the range of the data, and when you deal with extrapolations, they tend to be less accurate. Okay, because there's an underlying assumption here. The assumption is that you're assuming that this trend is going to continue in a linear path. It may not. It may trail off. It may suddenly increase. Any number of things could happen to this trend. Okay, so it's not a certainty that the trend will continue as in a linear path. So that's very important to note. Okay, so important. So that's an important thing to note. Example number 2. Let's look at another problem here. Okay, so researchers monitoring the number of wolves and rabbits in a wildlife reserve think that the wolf population depends on the rabbit population since wolves prey on rabbits. Over a period of 8 years, researchers have collected the following data. Okay, so we have some data here, and the data compares rabbit population and wolf population, and we're going to do the same thing. We're going to create some lines of best fit. Okay. What I'm going to do is pause. I'm going to stop the video here just for time constraints and space constraints. And if I don't create another video for the rest of the continuation of this example, I'll post the written solution to these examples for your own benefit, for your own study purposes. Okay, but you'll notice as I go through the rest of the filled in portion of this example, It's very much similar to what we did in the previous example. So look out for that.